Hello students, welcome back. We'll move on to the next problem on the bars. So here we have a steppered bar fixed at both the ends. Even this is completely fixed, even this is completely fixed, and the load has two cross sections. First is 250, the area of the first cross section is 250 mm square and the area of the second cross section is 400 mm square. In the first cross section, somewhere here, somewhere in the middle, a load of P is applied towards right, and there is no other loads here. The distance between the fixed end to the load is 150 mm, and from the load to the other step is 150 mm, and from this step to the fixed end is 300 mm. The question is, find nodal displacement, support reactions, element stiffness given P is equals to 300 kilonewton, E is equals to Young's modulus 200 into 10 power 9 Newton per meter square. Okay, we'll move on to the problem. So P is equals to 300 kilonewton, E is equals to 200 into 10 power 3 Newton per mm square. So given problem is this, convert that problem into FE model. So this is FE model as I've said in the previous videos. So finite element model. So how do you convert this into finite element model? So as I've said, wherever there is a fixed condition, there has to be a node. So there has to be a node wherever there is a fixed condition, and wherever there is a load, there has to be a node. So second node is at this point, and wherever there is a change in the cross section, there has to be a node. So third node is at this point, and wherever there is a fixed condition, there has to be a node. Okay, so there will be 4 nodes and 3 elements. So connect these nodes 1 and 2, you get first element, 2 and 3 you get second element, 3 and 4 you get third element. Okay, so as soon as you write this, write the boundary conditions. Write the boundary conditions. So first we have we have displacements and forces. So this is the displacements, the first one, and second one is the forces. Okay, so first the displacements, Q1, Q2, Q3, Q4 at 4 nodes. Next the forces, F1, F2, F3, F4, at 4 nodes. So first try to figure out the displacements. Q1. So Q1, the first node is completely fixed. The first node is completely fixed, so there won't be displacement. So Q1 is equals to 0. Coming to second node is not fixed. Okay, so there will be some displacement. We have to find the displacement. Just put a question mark. Coming to the third node is not fixed, so there won't be any displacement. Sorry, there will be some displacement. Since it is not fixed, there will be some displacement. So we have to find the displacement. Just put a question mark. Next, coming to the fourth node. Fourth node is completely fixed. Okay, fourth node is completely fixed. So since it is completely fixed, there won't be any displacement. So Q4 is equals to 0. Coming to forces, F1. Since F1, that is the first node, is fixed, because of the applied force, there will be some reaction force. Okay, so just write R1. Okay, coming to F2. F2, there is a force given here, P. Okay, P is the force given here in the positive x-axis, and the force value is 300 kilonewton. Just write it, 300 into 10 power 3 Newton. Coming to node 3. Node 3, there is no force given, neither it is not fixed. So force is 0, F3 is 0. Coming to F4, there is no force given, but it is fixed. Since it is fixed, there will be some reaction force. So write R4. Or in simple, wherever there is 0 in the Q, write the reactions. Wherever there is 0, write the reactions. And at the other stages, if there is a force given, write the force given. If the force is not given, write it as 0. As simple as that. Okay, next write the element connectivity table. So here we have 3 elements, 1, 2, 3 elements, 1, 2, 3, and the connection and the connectivity. This is the nodes. This is nodes. So first element is between the nodes 1 and 2, 1 and 2. Second element is between the nodes 2 and 3, 2 and 3. Third element is between the nodes 3 and 4. Okay, next step, similar to the previous problem. So we have the element stiffness matrix for a bar element. Ke is equals to Ae by Le, 1 minus 1 minus 1 1. Coming to the first element, K1. So coming to this first element is this one, from here to here. Okay, K1 is equals to A1 E1 by L1, 1 minus 1 minus 1 1. What is area of the first element? Is 250 mm square, and E is same for throughout the material or throughout the steppered bar, and L of the first one is 150 mm. Okay, so just substitute that. A is 250, E is 200 into 10 power 9 Newton per meter square. Convert that into 10 power into Newton per mm square. So it is 200 into 10 power 3 Newton per mm square divided by 150 is the length. Okay, this is positive 1 1 minus 1 minus 1 1. Okay, so take just keep 10 power 3 outside as common, multiply the whole thing inside the matrix. You'll get 333.33 minus 333.33 minus 333.33 333.33. Okay, now this is the K1 matrix, the first matrix. So first matrix for the first element is between the nodes 1 and 2. First element is between the nodes 1 and 2. So just number this 1 2 1 2 based on this element connectivity. Just look here, 1 2 1 2. Similarly, go for the element 2. K2 is equals to A2 E2 by L2 into 1 minus 1 minus 1 1. What is A2? Area of the second element. Area of the second element is same as the first element. Length is also same as the first element, and E is also same as the first element. So K2 will be similar to the K1. So you have the same thing, but only thing is, since it is K2, element 2 is between the nodes. Element 2 is between the nodes 2 and 3. So just number here 2 3 2 3 2 3 2 3. Okay. Coming to element 3, K3 is equals to A3 E3 by L3, 1 minus 1 minus 1 1. What is A3? Area of the third element. Area of the third element is 400, length is 300, E is same. So area is 400, length is 300. Sorry, length is 300 and E is 200 into 10 power 3. Take 10 power 3 as common, multiply all the things inside the bracket, you will get 266.66. Now third element, this is K3. K3 is between the nodes, is connected between the nodes. Third element is connected between the nodes 3 and 4. So just number it 3 4 3 and then 4. Okay, so now element stiffness matrix is done. Next is the global stiffness matrix. Global stiffness matrix, K is equals to K1 plus K2 plus K3. In the previous problems we had only 2 elements, so it is only K1 plus K2. Here there are 3 elements, so it is K is equals to K1 plus K2 plus K3. And what will be the size of the global stiffness matrix? You can see here it is up to 4. Okay, since we have 4 nodes here, it is up to 4. So just K is equals to, just draw a matrix of 1 2 3 4 1 2 3 4. Okay, and write the corresponding coordinates in the specific location. Now first write the first matrix. First matrix, K1 matrix. K1 matrix is in the coordinates 1 1 2 1 1 2 2 2. Okay, so starting from 1 1. Where is 1 1 here? 1 1. So that is in the first line. So just write this K1 here. Is this clear? Similarly, K2 starts from 2, 2, 2, 2. Okay, where is 2, 2 here? 2, 2. So start from here. 2, 2 is in the second line. Okay, so this is K2. This is K1. This is K2. Okay. Similarly, K3 starts from 3, 3. Okay. So where is 3, 3? 3, 3. That is this matrix. This is how you add it. Okay. Write the remaining things as 0. So here these two will be added up and these two will be added up. Here it is, you can see here 3, 3. 3, 3 is 333.33. Similarly here 3, 3 is 266.66. 333.33 plus 266.66 is nothing but 600. I've written directly here. This part I have added 2, 2 and 2, 2 of both the second and the first matrix. Okay. So upon adding and simplifying finite element equation, next step KQ is equals to F. This is the K matrix after adding the same matrix, K matrix. You can see here 10 power 3 is common as it is. Q values, where do you get Q values from? From this. So Q is 0, Q2, Q3, Q4 is 0. So just write as 0, Q2, Q3 and Q4 is 0. Similarly, F values. F values R1 310 power 3 Newton, 0 R4. R1 300 into 10 power 3, 0 R4. Okay. Using elimination method. So wherever there is 0 in the displacement, eliminate that row and that column. Here there is a 0 in the first row. Eliminate the first row and the first column. Next there is a 0 in the fourth row. Eliminate fourth row and fourth column of the stiffness matrix. Okay. So remaining is this one. Remaining is this one, this one and this one. So if you multiply it, so 10 power 3 into 666.66, this row into this column, 666.66 into Q2 is equals to, into Q2, then next plus minus 333.33 into Q3 is equals to 300 into 10 power 3. This will be the first equation. Next equation, 10 power 3 into minus 333.33 into Q2 plus 600 into Q3 is equals to 0. Is this clear? Okay, that's what the equation here. 10 power 3 is common. 66.66 into Q2 plus 333.333 into Q3 is equals to 300 into 10 power 3. Similarly, 10 power 3 is common. Minus 333.33 into Q2 plus 600 into Q3 is equals to 0. Just to solve these two equations simultaneously or in your calculators, you will get Q2, Q3. Two unknowns you have, Q2 and Q3. In both the equations you will get Q2 and Q3 as the solution. Okay. Q1 and Q4 it is already known from the boundary conditions itself. Okay. Next, the question is asked to find the reaction forces. Reaction forces, we have R1 and R4. So R1, to find out R1, the first equation, this into whole thing, this. 333.33 into 0 is 0, 333.33 into Q2 plus 0 into 0, 0 into 0. Okay, so it is just minus 333.33 into Q2 is equals to R1. So R1 is, okay, this is R1, sorry. Okay, so R1 is equals to minus 333.33 into Q2, so R1 is equals to 207.66 Newton. Similarly, R4. R4 is equals to 0 into 0, 0 into Q2, 0, minus 266.66 into Q3, this into this is 0. So only this into Q3 will be R4. Okay, so R4 you are getting it as this value, just minus 925 or minus 920.26 Newton. Next, find the stresses. Sigma 1 is equals to E1 by L1 minus 1 1 Q1 Q2. You are writing for the first element, so it is Q1 Q2. Okay, so just substitute the values E1 and L1 of the first element, minus 1 1, and substitute the values Q1 and Q2. Multiply this and this, minus 1 into 0 is 0, 1 into this one is this value, same thing, 0.623, and simplify this, you will get sigma 1. Okay, similarly sigma 2, E2 by L2 minus 1 1 Q2 Q3, second element. Writing for the second element. Second element is between the nodes 2 and 3. 2 and 3. Similarly, third element is between the nodes 3 and 4. So it is Q3, Q4. Okay. So second element is between the nodes Q2, Q3. Q2, Q3. Multiply this and this. First one in first column, you will get Q2 value as minus 369.33 Newton. Similarly, sigma 3 is equals to E3 by L3 minus 1 1 Q3 Q4, because third element is between the nodes 3 and 4. Similarly, multiply this and this, you will get Q3 value as minus 230.67 Newton per mm square. That's all as the problem. Next, we'll move on to the next problem. Quite simple problem. So one end is fixed. We have a steppered bar. So this is of a length of 50 mm, and second bar is of a length of 50 mm. Young's modulus is of the first bar is E1A1, Young's modulus and the area. Similarly, of the second bar is E2A2, and the force of compressive force F is equals to 10 kilonewton is given at this point. And the tensile force of, this is tensile force, and the tensile force of 5 kilonewton is given at the free end. Okay, E1 is 200 GPa, E2 is 70 GPa, A1 is 150 mm square, A2 is 100 mm square. So it is understood these two are the different material. Okay, write the finite element model. FE model. So wherever there is a fixed, we need a node. Wherever there is a change in the cross section, we need a node, and wherever there is a free end, we need a node. So since it is fixed, Q1, write this displacements and the forces Q1, Q2, Q3, F1, F2, F3. First Q1, it is fixed, so Q1 is equals to 0. Q2, it is not fixed, so Q2 we have to find out. Q3, it is not fixed, so there will be some displacement, so we have to find out Q3. Similarly, F1, since it is fixed, there will be some reaction force, that is R1. Or wherever there is a 0 in the Q, write it as reaction in the F. Similarly, F2. F2, there is a force given here at this point of 10 kilonewton, which is in the negative x-axis, so minus 10 into 10 power 3 Newton. There is a force given here at the node 3 in the positive x-axis, that is 5 kilonewton, so plus 5 into 10 power 3 Newton. Next is element connectivity. So element and nodes. There are two elements, 1 and 2. The first element is between the nodes 1 and 2, 1 and 2. Second element is between the nodes 2 and 3. So second element is between the nodes 2 and 3. Element stiffness matrix of a bar is Ke is equals to Ae by Le into 1 minus 1 minus 1, 1. So element 1, K1 is equals to You have to be very careful when the when the material is different, that is E1 and E2 is different. Usually you tend to make mistakes in this step. Okay, so write A1 of the first element properly. Similarly, E1 of the first element itself properly, and L1 of the first element properly. So this is A1 E1 by L1, 1 minus 1 minus 1 1, 10 power 3 common, just multiply the whole thing inside, you get 600 minus 600 minus 600 600, and it is between the nodes 1 2 1 2. Similarly, element 2 K2 is equals to A2 E2 by L2. Okay, you have to be very careful. This is A2 E2 by L2. You can see here A2 E2 by L2. Okay, so A2 E2 by L2, 1 minus 1 minus 1 1, and it is between the nodes 2 and 3. 2 and 3. 2 and 3 is also here. So 2 3 2 3. Okay, so this is K2. This is 2 3 2 3. Okay, take 10 power 3 as common, multiply everything inside, you get 140 minus 140 minus 140 140. So next is the global stiffness matrix. K is equals to K1 plus K2. Only two elements here. K is equals to 10 power 3 as common in both the thing. You write the size of the global stiffness matrix is 3. Okay. Maximum is 3 nodes. 1 1 1 1 is this one. Right. This is the first one. That is K1. Next is K2 starts from 2 2. So right from this one, this thing will be added. 140 plus 600 is 140 plus 600 is 740. Okay, this is clear. Next is finite element equation. KQ is equals to F. This is K. Q is 0. Q2 Q3. And F is R1 minus 10 to 10 power 3, 5 into 10 power 3. We have these values here, Q values and F values, which we have written here. Okay. This is 0, eliminate that row and that column. Since the first row is 0, eliminate first row and first column of the stiffness matrix. Next is multiply this row and this column. So 740 into Q2 minus 140 into Q3 is equals to minus 10 into 10 power 3. 10 power 3 is common in both the sides, so I've cancelled 10 power 3 here. Okay, even here there is a 10 power 3. So 10 power 3 and 10 power 3, I'm cancelling it out. Or if you want, you can write 10 power 3 here also, not a problem. Minus 140 into Q2 plus 140 into Q3 is equals to 5 into 10 power 3. 10 power 3 is 10 power 3 will be cancelled out. Okay. Solve these two equations, you will get Q2 and Q3. So Q2 is equals to minus 8.33 into 10 power minus 3 mm. Q3 is equals to 0.0273 mm. Okay, find the reaction. Only one reaction, R1, this row into this, that is 600 into 0 minus 600 into Q2, 0 into Q3 is equals to R1. So it is minus 600 into Q2, 10 power 3 common as it is. Be careful. So it is minus 600 into minus 8. Q2 is minus 8.33 into minus 10 power 3. You will get R1 is equals to 4.998 kilonewton. Okay. Next, stresses. Sigma 1 is equals to E1 by L1 minus 1 1 Q1 Q2. So we are writing for the first element. So E1 by L1 minus 1 1 Q1 Q2. E1 is equals to, multiply this and this, you will get E1 is equals to minus 33.32 Newton per mm square. Similarly, sigma 2 is equals to E2 by L2 minus 1 1 Q2, Q3. Multiply this and this. Just simplify. You will get sigma 2 is equals to 49.882 Newton per mm square. Okay. We'll move on to the next problem. The next problem is almost similar to previous problem, but instead of giving the area directly, he has given the diameter. Okay, so there's a stepped bar and fixed at both the ends. The first is steel, second is copper. So Young's modulus of the steel is 200 GPa, copper is 100 GPa. And the diameter of the first section is 60 mm, diameter of the second section is 40 mm. So first is steel, and here the load of 100 kilonewton is given at this point. Okay, and the length of the first bar is 800 mm and the second bar is 500 mm. Okay, so just write the finite element model. So wherever there is a fixed, we need a node. Wherever there is a change in the cross section, we need a node. Wherever there is fixed, there we need a node. So write the displacements and the forces. Displacements Q1, Q2, Q3, 3 nodes. Forces F1, F2 and F3. Q1, first node is completely fixed, so Q1 is equals to 0. Q2, second node is not fixed, so Q2 we have to find out. Q3, third node is completely fixed, so Q3 is equals to 0. Wherever there is a 0, write the reactions R1 and R3. Next, F2 is left out. F2, there is a force given in the positive x-axis, that is 100 kilonewton, so 100 into 10 power 3 Newton. Okay. Next, element connectivity. Element connectivity table, element and nodes. The first element is between the nodes 1 and 2. Second element is between the nodes first and the second. Second element is between the nodes 2 and 3. So 2 and 3. K is equals to AE by LE into 1 minus 1 minus 1. 1 is the element stiffness matrix. So here area is not given, diameter is given, so you have to find out the area. A1 is equals to pi d square by 4, d1 square by 4. So pi into d1 square is 60 square, you get area A1. Similarly, if you do A2, d2 square, you get A2. Okay. So element 1, K1 is equals to A1 E1 by L1. Okay. You have to be very careful. It is A1 E1. So substitute the value A1 E1, 200 GPa, so 200 into 10 power 3 MPa divided by L1. L1 is 800. Okay. 1 minus 1 minus 1 1. 10 power 3 is common. Take all the things inside. And write the connectivity. K1 is for between the nodes 1 and 2, so it is 1 2 1 2. Similarly, go for element 2, A2 E2 by L2. A2 is 1256.63, then E2 is 100 GPa, so 100 into 10 power 3 MPa, and L2 is 500. It is 500. 1 minus 1 minus 1 1. So it is K2 is between the nodes 2 3 2 3 2 3. Okay, 2 3 2 3. Next, write the global stiffness matrix. Ke is equals to K1 plus K2. So Ke is equals to 10 power 3 is common in both the matrix. Size of the matrix is 3 cross 3, because the maximum is 3 here. So wherever there is 1 1, so wherever there is 1 1, write the first one, and wherever there is 2 2, write the second one. Okay. So this will be added. Next is the finite element equation. KQ is equals to F. This is K. Q is equals to F. The similar Q is here, F is here. So Q is here, F is here. Elimination method, wherever there is 0, eliminate that row and that column. Here it is 0, this row and this column. First and third. Next. So just only one term is left out. This 10 power 3 is common. This into this will be equals to this. So you'll get only Q2. Similarly, find the reaction R1 and R3, this row into this. So no, not this into this, only this will be multiplied. Minus R06 into Q2 is equals to R1, so R1 is minus 73.77 Newton. Similarly, R3 you can find out like previous problems itself. Sigma 1 is equals to E1 by L1 minus 1 Q1 Q2. Substitute the values of Q1 Q2 for the first element. You will get sigma 1 as 26 MPa. Similarly, sigma 2 E2 by L2 minus 1 Q2 Q3, because this is for the second element. This is Q2 and Q3. Okay, this into this. So multiply this and simplify, you will get sigma 2 is equals to minus 20.8 MPa.